Hi everyone, and welcome to ILTA Physics Online. Today we're going to learn about circular motion, the motion of an object that moves along a circular path. Unlike linear motion, where an object moves in a straight line left, right, or up, down, circular motion involves a change in direction. This change in direction means the object is constantly accelerating, and that acceleration is what keeps it moving in a circle. You might wonder, how can acceleration make an object move in a circle? Don't worry, we'll figure that out step by step today. We'll first try to understand qualitatively, using diagrams, how an acceleration directed toward the center of a circle makes the object's path circular. We'll then derive the quantitative relationship between velocity and acceleration in a circular motion. This acceleration directed toward the center is called centripetal acceleration. When an object moves around a circle at a constant speed, we call that uniform circular motion. We'll explore how velocity and acceleration relate in this case. Circular motion is also a type of periodic motion, meaning it repeats in regular time intervals. So we'll also talk about the relationship between period and frequency with respect to the periodic motion. Finally, we'll consider the force that actually creates this centripetal acceleration, using Newton's second law, and solve a few simple example problems to make sure we fully understand the concept. There's a lot to cover today since this is a new chapter, so let's review some basic concepts before diving in. Before studying circular motion, let's quickly review a few physics concepts we've already learned that are related to this topic. First, acceleration is defined as the change in velocity over time. In equation form, that's final velocity minus initial velocity divided by time. Next, we have uniform motion, where an object moves with a constant velocity. Since velocity is a vector, it has both magnitude and direction. This means both the speed and the direction are unchanged. To distinguish it from circular motion, we'll call this uniform linear motion. We also need to recall Newton's second law, which describes the relationship between force and acceleration. It says that when multiple forces act on an object, the net force determines the object's acceleration and its direction. Remember how we used a free body diagram to analyze forces in horizontal and vertical directions separately? By finding the net force in each direction, we could find the acceleration in each direction as well. Here's an example of a free body diagram, a child riding a toy car being pushed by two friends. In the free body diagram, gravity acts downward, and the normal force acts upward with equal magnitude. Two forces by two friends push to the right, and friction acts to the left to resist to move. When we add all these vectors, we get the net force, which produces the object's acceleration. From a physics point of view, the relationship between velocity and acceleration belongs to kinematics, while the relationship between force and acceleration, Newton's second law, belongs to kinetics. When we combine both to describe motion completely, we call that dynamics. Looking back, we've really covered a lot of physics concepts and relationships, haven't we? I hope you try to understand them in a clear, organized way, not just memorize them. All right, now we're all set. Let's apply everything we've learned from the perspective of circular motion. Now let's finally talk about circular motion. Circular motion happens when the path of a moving object forms a circle. Because the direction of motion constantly changes, the velocity vector is always changing, and that means there's acceleration. So acceleration is what changes the direction of velocity, keeping the object moving in a circle. Let's look at the diagram on the left. Suppose an object is at the 3 o'clock position and starts to move upward. If an acceleration acts to the left, the resulting motion from upward velocity and left acceleration will be diagonally upward. At the next position, if acceleration acts diagonally downward toward southwest, the object's velocity will again shift direction. If this continues, the object's trajectory will form a circle. In the figure on the left, we've already taken a quick, qualitative look at how acceleration can combine with an object's velocity to change its path into circular motion. Now let's think a bit more precisely. In what direction should that acceleration act? We'll explain this using the middle figure. Imagine an object moving along a circular path, as shown in the diagram. To make things simpler, instead of drawing a perfect circle, we've represented the motion with 8 points, forming an octagon-like shape. Now, let's focus on the case where the object moves from point A to point B along the circle. Since it's already moving in circular motion, the object's velocities at points A and B, let's call them v and v2, have the magnitudes and directions shown in the figure. So, what kind of acceleration, meaning what direction and magnitude, must act on the object to make it move from A to B? Because acceleration represents the change in velocity, we can find it by taking the difference between the final and initial velocity vectors. If you calculate that vector subtraction, as shown in the figure on the right, you'll find that the acceleration points exactly to the left. If we repeat this process for every point along the circular path, as shown in the middle figure, we see that the acceleration always points toward the center of the circle. This center-directed acceleration is what we call centripetal acceleration. An interesting thing to notice is that, as shown in the left figure, the direction of the object's velocity is always tangent to the circle, while the centripetal acceleration is always perpendicular to it. So now we've qualitatively explained how centripetal acceleration, the acceleration directed toward the center, keeps an object moving in a circular path, and we understand its direction. In the next section, we'll figure out how to calculate the magnitude of that centripetal acceleration in a quantitative way. Now let's calculate the magnitude of this centripetal acceleration. Let's think about an object moving along a circular path from point A to point B, as shown in the lower left figure. For the sake of explanation, the 2 points A and B are drawn a bit farther apart than they actually are, but in reality, we can think of them as being very close to each other. That means the straight line distance between them, the displacement d, can be considered nearly the same as the arc length between A and B on the circle. In other words, we just drew them a little exaggerated for visibility, but if they're close enough, the arc AB and the straight line AB are practically the same. Now, let's zoom in on that part. As shown in the middle figure, if the velocities at points A and B are v1 and v2, then the triangle OAB, representing the object's position, and the triangle formed by the velocity vectors, UVW, are similar triangles. For two similar triangles, the ratios of corresponding sides are equal, and we can express that relationship with an equation. Since the displacement of a moving object equals its velocity multiplied by time, we can substitute that into the equation and get the following expression. Because acceleration is defined as the change in velocity over time, we can rearrange the equation to show that, in circular motion, the acceleration equals the square of the speed divided by the radius. This is the centripetal acceleration, often denoted as AC. We went through a fairly long explanation to derive this formula, but please make sure you remember this final result. The centripetal acceleration equals the square of the speed divided by the radius. And of course, don't forget that the direction of the centripetal acceleration is always toward the center of the circle and always perpendicular to the direction of velocity. Now let's summarize uniform circular motion. As we explained earlier, it's the centripetal acceleration directed toward the center of the circle that keeps an object moving along a circular path. Its magnitude is proportional to the square of the speed and inversely proportional to the radius of the circle. If the direction of velocity keeps changing due to this acceleration, but the speed at every point remains constant, we define that motion as uniform circular motion. In contrast, the uniform motion we studied earlier, more precisely called uniform linear motion, was when both the magnitude and direction of velocity stayed constant. As shown in the figure below, in uniform circular motion, the velocity is always tangent to the circle, while the acceleration is perpendicular to it, pointing toward the center of the circle. We can also describe circular motion from another perspective as periodic motion. Periodic motion is motion that repeats itself at regular time intervals. Examples include rotational motion and oscillations. We'll study this in more detail later, but such periodic motion is also referred to as simple harmonic motion. There are two important parameters to describe periodic motion: period and frequency. The period is the time it takes for an object to complete one full cycle along the circular path and return to its starting point. On the other hand, the frequency tells us how many cycles are completed in 1 second. Since the period is the time for one cycle and frequency counts how many cycles occur in a second, they are naturally reciprocals of each other. Now let's use period and frequency to express the speed and acceleration of the uniform circular motion we learned today. First, speed or velocity magnitude is defined as distance divided by time. Consider the example in the figure on the right. A fly sitting on a turntable completes one full rotation and returns to its starting point. If the time it takes for the fly to complete one circle is t, the distance traveled is the circumference of the circle, calculated as 2 pi r, where r is the radius. So the speed is the distance divided by the period. And we can also express this using the frequency as follows. Since the centripetal acceleration is defined as the square of the speed divided by the radius, we can substitute the speed we just calculated and simplify it to get the following expression. Therefore, in uniform circular motion, if we know the period or frequency, we can calculate both the speed and acceleration of the motion directly. Earlier, we explained that centripetal acceleration keeps an object moving along a circular path. But then the question arises, where does that centripetal acceleration come from? The wording might sound a bit odd. According to Newton's second law, we learned that an external force is what accelerates an object. In terms of the formula we memorized, that's F equals ma. If multiple forces act on an object at the same time, the net force, the vector sum of all the forces acting on the object, produces the acceleration. Applying this to circular motion, since centripetal acceleration produces the circular motion, there must be a force that causes this centripetal acceleration. This force is what we call the centripetal force. As shown in the figure, suppose an object at a certain position has a velocity pointing tangent to the circle, upward in the figure. If there is a net force directed toward the center of the circle, this force produces an acceleration in the same direction, the centripetal acceleration. This centripetal acceleration then changes the direction of the object's velocity, keeping the object moving along the circular path. The magnitude of the centripetal force can be calculated using Newton's second law. We simply substitute the centripetal acceleration, the square of the speed divided by the radius, into the formula F equals ma. Alright, finally, let's solve some basic problems on circular motion together. The problem is about a car moving along a circular track, as shown in the figure on the right. We have a 900 kilograms car moving at a speed of 25 meters per second along a circular track with a radius of 50 meters, and the question asks us to calculate the centripetal force acting on the car. First, the acceleration in uniform circular motion is the speed squared divided by the radius, and using Newton's second law, the relationship between force and acceleration is F equals ma. So the centripetal force, Fc, can be calculated by plugging in the values into the formula. When we do that, the result is 11,250 Newton. This is a simple calculation problem using a formula, a basic type that connects kinematics and kinetics. The next problem is a bit more complex, but is also a typical, frequently tested type of question. Assume the same circular track is flat, and we are asked to calculate the coefficient of static friction between the car's wheels and the road so that the car can make the turn without slipping. At first, it might seem a little vague, but this is a classic dynamics problem, so let's think through it step by step. To analyze this motion, let's draw a free body diagram. A top view, like the one on the right, helps visualize the circular motion in a space visually. However, to show all the forces acting on the object, it is more effective to draw the free body diagram from a horizontal perspective, as shown in the lower figure. From this horizontal viewpoint, gravity acts downward toward the center of the Earth, giving the car a weight. The normal force from the road acts upward, balancing the weight. As the car moves along the circular track, there is a tendency for it to slide outward. To prevent this, a static frictional force acts inward toward the center of the circle. Now, think carefully. Why do we consider static friction instead of kinetic friction for a moving car? Yes, although the car is moving, its motion along the track is tangential, and the friction we are considering is the force that prevents the car from sliding outward, which is static friction. Returning to friction. The frictional force is calculated as the coefficient of static friction times the normal force, and since the normal force equals the car's weight, it is mg. There are no other forces acting in this horizontal direction. Remember, this problem is about the car attempting to slide outward in the northwest direction on the curve, and the friction force acting southeast preventing that slip. From the free body diagram, the net force acting on the car in this horizontal direction is the frictional force, which must equal the centripetal force we calculated earlier. From this relationship, we can express the coefficient of static friction. By plugging in the numbers, the coefficient comes out to 0.13. It's important to practice approaching and thinking through problems like this consistently. That brings us to the end of today's lecture. Great job, everyone. See you in the next class.